that you would like me to go over. It didn't help as much as I thought it would. That's electrochemistry. So if we look at the review, were there any review questions that you particularly wanted me to deal with in terms of electrochemistry? We did one of these together, and I've actually decided to put them on the screen for us to see. So that should be some help, I guess. I don't know. Hopefully it is. I can't find my paper here. Here it is. Are there any of the electrochemistry questions that in particular you wanted me to go over? Or did you feel pretty good about the electrochemistry questions? Felt pretty good? If so, we will move on, and we need to talk today about kinetics, right? And I'm somewhat tempted to kind of do turbo teach and do kinetics and atomic theory because we're kind of a day behind due to the snowstorm. Okay, then I will trust that you're doing well on those. Let's talk about kinetics here. So let's just do some general review. Remember, get our brain cells firing. What is kinetics studying? What is it that we're attempting to learn? What is kinetics? Kinetics is studying how fast a reaction takes place, right? It's how fast a reaction takes place, right? So we're talking about the speed of a reaction. Now, we can talk about this conceptually. How do you increase the speed of a reaction? All right, you can increase the temperature, and if you increase the temperature, what does that do? Say again? Makes it go faster. Okay, that's true. I need you to be more specific. Why does it make it go faster? You have more energetic molecules. Basically, we should back up here. Why do reactions happen? Or what causes them to occur? What causes them to occur? A what? A collision, right? How do you get a date for the prom? Got to hit them in the books, right? How was the prom, by the way? Good prom? Good. All right. Everybody, prom was, it wasn't what you hoped it was going to be? Oh, good. Oh, bummer. Even at the Air Force Academy, it was not so good?
It was like in the press box. I thought it was going to be like in like, I don't know.
Okay. All right. Well, anyways, you got your dates, though, right? Because you hit them in the books, right? Okay. So you got this collision thing going on. So if I want to make a reaction happen, the molecules must collide. And to make it happen faster, they must collide either with greater energy or with greater frequency, right? And so increasing temperature actually is the one thing that does both. You get more energy and you get more collisions, or with greater frequency. This is such, if they're going to ask you a kinetics question on the exam that's conceptual, it's all about this. If you know how to get a date for the prom, as we talked about, then you're good, all right? Those people in the podcast world are going to go, what is he talking about? Okay, increased temperature, what else? You can add a catalyst. Now, what does a catalyst do? Lowers the E sub A, the activation energy. We can draw a little graph. Right here's the graph of the reaction pathway, and it's going to lower the activation energy. Now, how does it lower the activation energy? It changes the mechanism. That's the steps, which we call the mechanism. Right? So we can do it by that. How else can we change the increased temperature? Add a catalyst. We could increase pressure. And when you increase the pressure, if you think of it from a perspective here I have some molecules. And then if I increase the pressure, that'd be like by decreasing the volume. The way we get the date for the prom is I talked to Miss Spry, and she puts a bunch of things in the hallways, like furniture. And so now what are you going to do? you're going to be closer together, so you're going to what? More collisions, right, or more frequent collisions. So the reason that increasing the pressure is because you get more collisions. What else can we do? So we've done temperature, pressure, catalyst. Add more reactants. So you got a picture like this, 5 molecules. Those are all like circles there. All right, and then if you inject into here a bunch more molecules, you will have, of course, more collisions again, don't you? All right, we're missing one. What else can you do? Yeah, that's like, you know, you can take away some of the product. I guess that would work. What's going on there? Okay, anything else? You girls travel in packs. So that's analogous to what? Surface area. If you want to increase the rate of reaction, then you need to increase the surface area. That means to powderize, pulverize the substance, right? So if I have a cube of sugar and I want to increase the rate of it dissolving, how could I'm going to put it, you know, in a cup of coffee, right? That's a cube of sugar. That's a big piece of sugar. What would I do? You would smash it up, and then you would have lots of little cubes of sugar, and that gets placed in the coffee cup, and it will dissolve much faster. That's because if you think about it, what surface on the cube can be exposed? Well, just the surface of it, right? But if you pulverize it, each little piece has its own surface, and so the surface area of a cube is much, much smaller than the surface area of the cube pulverized. Therefore, it will react very, very fast. Ringing bells? And again, so what's going to happen? What's the reason here in terms of collisions? More collisions or more frequent collisions? More collisions. All right, more collisions or more energetic collisions. More collisions and more frequent collisions is saying the same thing. So, okay. So you get more collisions, don't you? Because there's just more surface to hit. Good? All right. So that's the conceptual stuff. If you can explain that, that really, if they give us a conceptual question, those are really kind of easy questions. Okay? But there's also this sort of reaction mechanism thing. So let's say we got a reaction. Let's talk about mechanisms for a while. It seems like they always throw a mechanism question in there, regardless of whether it's a mathematical one or a non-mathematical one. So let's say with the reaction A plus B, let's say this is fast equilibrium makes C. This is fast equilibrium. This is step number 1. Step number 2 is C plus D makes E. And then E turns into, and this will be slow, E turns to F plus B. Did I do that right? Hold on, let me think about this for a minute. No, I think we'll do this. That'll be fast. Cut out the B there. Okay. First question they're going to ask you, what is the reaction? What is the overall reaction? Or sometimes they'll say, what is the stoichiometry of the reaction? So what is the stoichiometry of this reaction? Anything cancel out, basically. C cancels out, and E cancels out. So basically your reaction is A plus B plus D makes F. Okay, what would be the rate law for this reaction? Remember, rate equals K times something, right? Now, it's always based upon what step? The slow step, all right? So if you think about it, the rate would actually be equal to what? C times D. But the problem with saying the rate is equal to K times C to the first and times D to the first is that C is not a reactant. C is a intermediate. So you can't have an intermediate in your rate determining step. But by knowing that this is fast equilibrium, the double arrow, what do we know C is basically equal to? A times B, right? So from substitution, we can substitute A times B into C. So the rate would be equal to K times A times B, that's the C term here, right, times D. All to the first power in this case. Okay, does that ring bells now? How you would do this? Invariably, they want to put one of them equilibrium ones, which makes it kind of hard. But it's always the slow step. But if you've got an element or a compound, whatever, in the slow step, it then is invariably equal to something else, usually a couple of things. It could be like A squared, or I don't know, it could be lots of things. Okay, good. Now, what about the mathematics of all this? Give us some mathematical kinetics questions, which they could certainly go down that road. So if you've got a mathematical question, all right, first of all, there is a series of equations at one point that you've memorized. And you don't necessarily need to memorize these because they'll give you the equations on the exam. But we know that rate is equal to, well, let me back up. There's first order, there's second order, and there's zero order. All right? And there's several equations. Here, rate would be equal to K times the concentration of A. This is rate equals K times A squared. And here, rate equals K. The half-life is equal to 0.693 over K. The half-life of this one, I always forget. So we should fill those in and whatever. This is where you plot a graph of the natural log of A versus time, gives you a straight line. This is 1 over the concentration of A versus time, and this is just 1 A versus time. These two are the ones that are most likely going to give you the deal there.
Do we need to memorize the parts that we don't know? We don't?
Yes, you probably should. Especially, I've never seen them put this on the test. And then there's the natural log of A is equal to negative KT plus the natural log of A0. And this is 1 over A is equal to KT plus 1 over A0. And this is just A equals, I don't know. If you got your book, it's on like page 500, and I'm trying to copy this from memory, and I'm probably not going to be very good at it. I'm going to miss an equation. Didn't I give you in the packet a list of all the equations? Surely I did. If I didn't, I will definitely do that. Maybe I'll do that this hour. Huh? Did you guys get a list of all the equation sheets? All right, so it's on page 500, and I don't know. Did somebody get their book and open it up, or did you not bring it today? It's in chapter 12. Here's my book right here. I want to say 560. No, 3. I don't know. No, 500. Yeah, 567. Nope, I'm close though. The key table on all this stuff. 582, you said? No, it's not 582. What did you say? 572. I'm sorry. Yeah, bottom of 572, table 12.6. That's got all those equations that you want to know. Okay? Now, with that said, if they give you a mathematical question, the most common mathematical question that you're going to get is using what we are all-day lab. It's this, the method of initial rates. And these are relatively easy, right? Remember, you got experiment 1, experiment 2, experiment 3. You got A, and you got B, and you got rate. This is 1 molar, and the rate is 3. All right, this is 1 molar, 2 molar, and the rate is 6. And then this is 2 molar, 4 molar, and the rate is 6. I don't know. Remember how we would do this? This is ringing bells here. They'll have a little bit more specific numbers. You'll just take E1, actually take E2 divided by E1, and remember K times A times B. This is to the X, and this is to the Y, etc., right? And you solve for X, and you solve for Y. And then eventually you solve for K. Now you got to watch the units on K. Depending on what the order of the reaction is, the units invariably change, and they always ask the question, what are the units on equilibrium constant K? Good? That's just a reminder of how to do these. There has been a couple of years, actually in relatively recent history, where they've made you go back and not mathematically. Remember how we would solve, is it first order, is it second order, basically giving you a table of data, and we'd utilize, basically we plugged it into our calculator, and we said, used our correlation factor to find out what that was. Remember how that was, those questions? Well, but you had a table of data, so you had time and concentration data. You had a bunch of time, 1, 2, 3, 4, and these were different concentrations. And then you created stat plots in your graph where you did natural log of concentration, and you did 1 over concentration in your calculator. And the one that yielded the straight line was the winner. Now, they've never asked on the exam students to actually physically do this. But what they have asked is for you to describe the process, which I think is almost harder. Basically, you would say, well, I would plot a graph of natural log versus time, and if that gave me a straight line, it would be first order. And if I got 1 over concentration versus time, that would be second order. All right, so you'd have to describe the process instead of do it. The reason that is that a lot of, frankly, I think a lot of teachers may not know how to use the statistical features of the graphing calculators, and they, I think, probably are also realizing that many students may not have a graphing calculator, and they may not know how to use it. And so therefore, they've made you describe it as opposed to do it. So that's kind of where I've seen a trend on those types of questions. So there's 2 types of questions, kinetics mathematically. It's this kind, but this one is usually written conceptually, and then there's the method of initial rates. Okay? So speaking of that, let's take a look at some of the kinetics questions. I'll have to find one here. I thought I could see them. Oh, it didn't convert it. Okay. This looks like a good one. Let's go with this one. So let's turn to this one, Review 22. Let's see if we can do Review 22 together. This is going to be one of those method of initial rates. So I didn't do a sample problem because I figured we'll just do one of the reviews that are already printed in our packet. All right, the following results were obtained. Here's our reaction. 2A plus B makes C and D. Here's several experiments and some numbers. Determine the order of the reaction with respect to A and B. So why don't you get a blank sheet of paper out and then say review number 22. And we'll see if you can do part A now on your own. And I'll come around and help you as you need it. And then we'll do it together. So see if you can do review 22, 1997 question. These problems are a little bit long and complex, aren't they? So what I would do, I'll just set it up here and you can kind of watch me, or I'm going to do part A at least. Rate would be equal to K times A to the X, B to the Y. So I'm going to do divided by E1, 1.3 times 10 to the minus third is equal to K times 0.75 to the X times 0.75 to the Y, that's K, 0.25 to the X, 0.75 to the Y. The Y's cancel, or the 0.75s, and then I can do this in my head. That's going to be 3 to the X would be equal to, oops, I forgot to put this, was 4.3 times 10 to the minus fourth. Is this 3 by chance? Yeah. So what is X? 1. All right. That gives me X. I got to find Y. So how am I going to divide by Y? Is there any way to get them to cancel out? Huh? There isn't. That was so mean of them. So what do I have to do? I just got to pick 2. I already know what X is. X is 1, right? So when they give you one that's kind of ugly like this, then let's take experiment. I'm going to do 3 divided by 1. I don't think it really matters. So E3 over E1. So experiment 3 took 5.3 times 10 to the minus third. Experiment 1 was 4.3 times 10 to the minus fourth equals K. Now the 5.3 number is going to be 1.5. But watch what I do. It's to the first power, right? Times 1.5 to the y power. I don't know what y is, but I can do it mathematically. And then the K will be equal to 0.25 to the first times 0.75 to the y. Now mathematically, 1.5 over a quarter is at 6. Yeah. So this, the k's do cancel. So this is 6 to the first. What's 1.5? That's 2, right? Is equal to 2 to the y times 2 to the y. Would be equal to, did somebody do the math on this? What's this come out to be? 12. So I'm running out of space. So 12 equals 2 to the y. So if 12 is equal to 6 times 2 to the y power, what do? Divide by 6, right? I get 2 is equal to 2 to the y. Y equals 1. Good? A little tricky, wasn't it? But it wasn't horrid. Write the rate law for this reaction. Well, that's easy. Rate would be equal to what? No, it's going to be first order with respect to A and with respect to B, but second order overall. Determine the order. Okay, good. Order is second order. Oh, wait. Determine the order of the reaction with respect to A and B. You know, I would say, I'd be more implicit. I'd say it is first order with respect to A. It is first order with respect to B. I would be redundant here and say it all, you know. Calculate the value of the rate constant. What do? You just pick an experiment. I like experiment 1 because it's the first one. I don't know. I'd say 4.3 times 10 to the minus fourth is equal to K. That's what I'm trying to find. Times 0.25 to the first times 0.75 to the first. Well, you just divide both sides by 1/4 and 3/4, and somebody maybe, I let my good calculator out. So 4.3, different calculator than I'm used to. There it is, -4. Divided by 0.25, divided by 0.75. I get 2.13, is what you got? Times 10 to the minus third. Now, what are the units on this going to be? Now, that's always the tricky part, the units, right? Now, what are the units on rate? It says moles per liter per minute, or molarity per minute, right? Well, that equals to K times molarity, right? So what do the units on K have to be if these are both molarity? Well, minutes has to be on the bottom. And then you got to have what? No. The molarity on the bottom. So it's 1 over molarity minutes, or we would say molarity minus 1, minute minus 1. Right? Remember that, how that works in mathematics? That would be the units. Or you could say liter per mole, that's opposite of molarity, right? Minute. All right, not too bad. If we get a question like this, they're not horrid, are they? Question C says, determine the rate of change of A in experiment 3. The initial rate of change of A in experiment 3. So if we look at the experiment 3 data, what is the rate of change of A? What do you know about A, or experiment 3? We know the concentration of A is equal to 1.5. Concentration of B is equal to 1.5 moles per liter, I assume. Yeah. So we have our equation. Rate is equal to K. Now, what was K again? 2 point something. What was it? 2.13 times 10 to the minus third, I think, right? Times the concentration of A
times the concentration of B. Well, we know A and B is 1.5, so it's 1.5 and 1.5. So somebody with a calculator, what is the initial rate? Not necessarily. Hold that thought. Yes, actually it would. Do you get 5.3 times 10 to the minus third? You better, or we done it wrong. Yeah, I'm overdoing it. Better be this. Do you get that? You better. Or we've done it totally wrong. But it says, what's the rate of A? What is this rate? Take a look at the data table. What are they measuring? What is this measuring? Rate of what? Look in the data table. At the top of the data table for the rate, the 5.3. It's the formation of C. Now take a look at the balanced equation. 2A plus B makes C and D. We're measuring how fast C gets formed. A will disappear at what ratio of rates? What do you do with this 2 and the fact that there's a 1 right here? Half or double? It's double. Because basically this number here is 5.3, and that's C, times 2A over C. The C's cancel. It would be double. So it would be 10.3, or 10.6, times 10 to the minus third. In other scientific notation, you could say 1.06 times 10 to the minus 2, I think is how it would be, right? Or 1.06 times 10 to the minus 2 molarity per minute. That's how fast A will disappear. Do you see why it's double instead of half? And that's a tricky question. It had nothing to do with plugging it in and doing this. That was a waste of time. My mistake. Okay. Determine the initial value of B in experiment 4. Now that's not too bad. That's where equation, right? We know the rate is 8.0 times 10 to the minus third is equal to 2.13 times 10 to the minus third times 1.75 to the first times x to the first. So 8 exponent minus third divided by 2.13 exponent minus third divided by 1.75. I get 2.15. Concentration of B is 2.15 molar. And then the big question, letter E. All right, what in the blazes is that? Letter E. We got a bunch of reactions. Now, overall, we learned that the rate is equal to K times the concentration of A times the concentration of B. So now, which one of these best represents our reaction? A little bit of typographical errors I see here. They've got this little box is a double arrow probably. If I were to do reaction mechanism 1, the slow step is M times A, right? And M is going to be equal to A times B plus over C. That's going to be nasty. I'm guessing no on this one. Okay. Reaction 2, my slow step is M times A. I like this one. It's 2. Okay, why? Because this is that double arrow. Look at 2. B goes to M, and then M plus A goes to C plus X, and A plus X goes to D. Actually, I better double check that it works, and this is your slow step. So the rate here would be equal to M times A. But what is M equal to? Oh, B, this should say M here. B equals M, right? And so if you plug the B in, then that's it. Now make sure that everything cancels. The M's have to cancel. I better get 2A plus B makes C plus D, and the X's cancel. Yeah, it does. So do this, and you have to show this work here. If you say, I like number 2, you get 0 points, even if you're right. You've got to justify your choice. Sorry. Yeah, they don't just give you credit for that. No. You can't. The guessing is not. On the multiple choice, you could guess and get points because it's multiple choice. But for your response, it says justify. Without justification, you get a 0 points. You might check the other one, but if you were to do this one, fast equilibrium, so you've got A and B. This is your slow step, so M times A. Yeah, that's not going to work. Okay? Does that ring a bell? Remember how to do all these varieties of questions? Let's do review 23, and then we'll call it good for kinetics. All right. It's all conceptual here. You might get a conceptual question. You might get a mathematical question. There's one of each variety, right? Who knows what you're going to get. Okay. On 23, it says the reaction between nitrogen monoxide and hydrogen is believed to occur in the following three-step process. Again, this is probably supposed to be a double arrow right here. Some typos here. Okay. Write the balanced equation for the overall reaction. That means just cancel things out. So what can you cancel out? Into O2, into O, so you're going to have NO plus 2H2 makes N2 plus 2 H2Os. Did I make a mistake? What? Where you circled the box that you blocked. Oh, there's 2 NOs, aren't there? Huh? Why'd they separate the 2 NOs? Because they want to show that they're colliding. Okay, good question. In fact, we didn't use this term, but we would say that the first step is bimolecular. Remember that? And in fact, all 3 steps are bimolecular, where there's just one thing. If you've only got one step, it's unimolecular, and then termolecular is very unlikely, which is 3 things hitting. Identify the intermediates in the reactions. Which ones are intermediates? This case does, oh, and it says explain your reasoning. Okay, got to explain it here. Intermediates are things that appear on a product side and then disappear. So what does that? Into O2 and into O. That's because, again, I would say they appear as a product and then disappear. Now, how does that differ from a catalyst? They appear as a reactant and then disappear. There are no catalysts in this particular reaction. Okay? From the mechanism above, a student correctly deduced that the rate law for the reaction is there. The student then concludes that, number 1, the reaction is third order, and the mechanism involves the simultaneous collision of 2 NO molecules and an H2 molecule. Are collisions 1 and 2 correct? Okay. What is the rate law of this reaction is what they're asking. All right. He correctly deduces, so they're saying this indeed is the mechanism. Is it third order? Yes, it's third order because it's second order with respect to nitrogen monoxide and first order with respect to hydrogen, and they add together. I think you're going to have to say that. So write that down. I mean, it's third order because when you add the exponents of all the things in the rate law, they add up to 3, right? Now, how about number 2? Is he correct about number 2? His second assumption is the mechanism involves the simultaneous collision of 2 NO and an H2 molecule. So what he's envisioning is you've got the NO, and the H2, and they all must come together at one time. Is that correct? No. Because what's the slow step? It's the second step here. It's the N2O2 plus the hydrogen, because that's the slow step. Now, the N2O2 is actually equal to NO plus NO, but that happens very quickly, right? So he's wrong. What you're actually, what's the slow step is the intermediate N2O2 colliding with the H2. And the only reason we put the NO in the rate law is because there's a very quick reaction to produce the N2O2. So I would, again, write that all out. So you see what that, I would doubt that they'll be right about both assumptions if they give you a question like this. You should be very leery. Oh, he's right on both accounts. Done, period. No. They're not going to do that. They want you to discover the error of the child's ways. All right. Letter D, not bad at all. Why does the increase in temperature increase the rate constant? More energy and more collisions, just like we talked about at the beginning of the lecture, right? More collisions, more energy, makes faster reaction, which makes the K go up. So the value of the rate constant is constant only as long as you are at a particular temperature. If you raise the temperature, the reaction will happen at a more elevated temperature. Good? All right, we're going to do turbo teach here. All right, let's do